University. Carolyn got her PhD with Bill Lobel in Montreal, followed by a postdoc with Ron Zuckerman. And the title of her talk is New Strategies for Ketoxime Peptide Ligations. Carolyn.
All right, thank you for the introduction, and it's going to be a little bit hard to follow the karaoke, but I'll try my best. And thanks for the audience for sticking around. And so I'll be telling you about what my lab has been up to at NC State University for the past 3 years, and we've been focused on doing some methodology development, working, and specifically what I'm going to tell you about today is a new strategy for ketoxime ligation, starting from N-aryl peptides to simplify the process under mild conditions and keep side chain diversity at the site of ligation. Okay, so just a little bit about why we're interested in it. So oxime ligation has found some widespread utility, both to intramolecular variations and intermolecular variations. Here we're looking at an example of replacing the disulfide bridge of oxytocin with an oxime linkage. And so typically what happens, I don't know if this pointer is working very well, but what happens that you install an amino oxy residue and a serine residue, and then you then oxidize the serine residue with sodium periodate to get an alpha oxoaldehyde. And then this undergoes a chemoselective ligation to give your oxime bridge. Some more recent work has shown that macrocyclic oxime bridge peptides can tolerate secondary structures such as beta turns, and work of Seth Horn here shows that you can stabilize macrocyclic alpha helical conformations and peptides increase the melting temperature if you incorporate these unnatural amino acids at the I and the I+4 positions. A lot of applications for oxime ligation also exist in the intermolecular size of things, and so we're looking at an early example from Steve Kent's lab that utilizes oxime ligation in the context of total protein synthesis. You can use oxime ligation as well to make multifunctional constructs. We're looking at synthetic vaccine examples. Another thing I really want to point out is oxime ligation is essentially a orthogonal, bioorthogonal ligation tool, which means that you can do it at the same or subsequently after doing some azide-alkyne cycloaddition reaction. These are compatible with one another, and so that makes it orthogonal, bioorthogonal ligation here. And here's an example. We've heard a little bit about phage display. Here's a work of Radmir Durda utilizing oxime ligation reaction directly on these phage displayed peptide libraries. So a lot of application for oxime ligation. My lab is really interested in and focused on developing or improving the methods for that chemistry specifically. So if we take a look at oxime ligation reaction in the context of other types of bioconjugation techniques, I've mentioned before azide-alkyne cycloadditions. We've got the fastest bioconjugation up here, trans-cyclooctene cyclizations. If you place that in oxime ligation in the context of these, they're much slower. And so typically, what you would have to do to get decent reaction rate, reaction kinetics, is to bring the pH down to 4.5. And so this is a little bit not necessarily ideal. And so the work of Phil Dawson has really nicely addressed that limitation to get decent reaction rates at pH 7. And he has shown that you can do that if you simply add superstoichiometric amounts of aniline catalyst to your ligation reaction to get a aniline Schiff base intermediate. That intermediate is now more readily protonated at pH 7, which allows you to do this chemistry at neutral pH and improve the reaction rates at neutral pH. So right now, chances are if you are doing oxime ligation reactions, you are doing it under aniline catalyzed conditions to be under neutral pH. Okay, so since the publication by the Dawson Lab in 2006, there's been a lot of new catalyst development, all based on this aniline or slightly varied scaffolds, but similar purpose to get these readily protonatable Schiff-based intermediates at neutral pH. So you're looking at a few examples here, just varying the electronics, the substituents around the ring, including proton donors, and so on and so forth. And there's a really nice review that was published in ChemRev in 2007 by Eric Kuhl that addresses this type of chemistry, if you're interested. Okay, so at point, I want to introduce what the existing or remaining challenges with oxime ligations are. And so we are, again, state of the art is to do this under aniline catalysis at neutral pH. One thing that I want to point out is that if you want to do these types of ligation in live cells, 100 millimolar of aniline catalyst can be toxic to cells. And so that's one problem. If we could eliminate that, that would be great. But as a synthetic chemist, another really important challenge that we wanted to address was the step, which this was working, but the first step where you expose a serine residue to sodium periodate to get to your alpha oxoaldehyde substrate. So now this step can be problematic if you have residues that are sensitive, such as tryptophan, methionine, cysteine, etc. You have to control precisely the number of equivalents, the reaction time, etc., to avoid oxidation of these side chains. And the other thing that you'll notice, which will become important for us, there's really no way to control or trigger this oxidation under variable conditions. You either expose your serine-containing peptide to sodium periodate or you don't. And so this is something that we would like to address as well. And finally, the last point here is considered, oxime ligations are currently considered to be biorestricted. And the reason for that is that you have other aldehydes in the cells, and so it's difficult to do chemistry selectively on this alpha oxoaldehyde in the presence of sugars and cofactor aldehydes and all those things. So our approach has been to try to access the same critical alpha amino amide intermediate that we know is really important to do this reaction at neutral pH, but to get there in a different way. And so what we've been thinking about is starting from an N-terminal anaeryl peptide and see if we can site-selectively oxidize this under mild conditions to the same alpha amino amide intermediate that Phil Dawson is getting when he's treating his alpha oxoaldehyde with aniline catalyst, and then you can perform that oxime ligation under neutral condition. So again, just to point out, that would be the same reactive intermediate, but we would now be in a 2-component system instead of a 3-component, so essentially this would be catalyst-free. And if we can do that without chemical oxidant, I'll show you in a little bit that that's possible, then that would definitely be milder. And something that I was really excited about is this tunability potential. As you can see, I put an R group here on the anaeryl ring, so that means if you tune the electronics of that ring, you might be able to access a different libraries that can be triggered under different conditions to get to this critical alpha amino amide intermediate. Okay, so we were actually inspired by chemistry developed by C.J. Lee over at McGill that had shown that you can do site-selective oxidative couplings onto N-phenylglycinyl type of derivative. And so that work, if you notice, has then been followed up in the past 10 years by other publications to do these site-selective carbon-carbon bond formation on these N-phenylglycine derivative. But if you notice the conditions under the arrow, typically you require stoichiometric amounts stoichiometric amounts of chemical oxidant, for example, tert-butyl hydrogen peroxide, metal, copper bromide, etc., organic solvent, of course. So if I go back a slide, we really want to be able to do this in the context of bioconjugation, mild conditions. So we've got to get rid of all these chemical oxidants and hopefully be able to do this under mild conditions in water. So I'm going to focus in on these 2 reactions that were published in 2014 that actually show that you can do, again, a site-selective carbon-carbon bond formation on an N-phenylglycinyl derivative. But what got us excited is that you can do this under just air, oxygen, no chemical oxidant in this specific case, but very specific solvent, organic solvent ratio, as you'll notice, 5:1 acetonitrile DCE. And it turns out if you read this paper carefully, that 5:1 ratio is really important, and the trace amount of HCl, if you're using undistilled DCE, is very critical here. So our question was great, we can probably get this done under oxygen atmosphere, but how acidic do we really need to be, right, to get this reaction to go and to trigger this site-selective oxidation? And so the first thing that I asked my very first graduate student to do in the lab is to just make a test peptide, LYRAG in this case, with a wide representation of different side chain. We made this, we installed the N-phenylglycine via what we call peptoid submonomer procedure, in which we bromoacetylate the growing resin-bound peptide, followed by a simple SN2 displacement reaction with paramethoxyaniline. We have our N-phenylglycinyl peptides. We cleave that off of solid support, and we can start seeing how that behaves in different buffer solution. So really easy, really simple synthesis of these types of substrate. I'll mention that we started with the paramethoxy substituted aniline simply because of the organic, if I go back a slide, all of this work, most of this work has been done where R1 is equal to a methoxy group. A lot of the aniline catalyzed work has also been done with paramethoxyaniline, so we started off with this substituent. All right, so then I asked my student to treat that peptide in the presence of a simple amino oxy with a UV handle here, O-benzyl hydroxylamine, open to air in different pH, and to just see if we were able to convert our anaerobic peptide into the desired oxime ligation reaction. And we're actually pleased to see that it does happen, and it happens very cleanly, and that is for pH 4.5. So if you're at pH 4.5, you get a selective, very clean oxidation, followed by an oxime ligation all in one pot. The only peaks that we are able to detect by HPLC is unreacted N-phenylglycinyl peptide and our desired oxime product. But if you notice right away, what happens is as we're getting closer and closer to neutral pH, that oxidation is shutting down. Okay, so not great. It is, again, very mild, but we're almost back, not quite, but almost back to square one because we're at pH 4.5, which were the conditions that you needed to get these oxime ligation to go without the aniline catalysis, right? And so we did, I guess, the somewhat obvious thing, and we modified the electronics, which is what I really like about this strategy, is this fine-tuning of the electronics of the N-aryl ring. And so we made a bunch of analogs with di or tri-substituted methoxy rings, and we made the analog that had a very electron-rich dimethylamino group at the para position, analog 1F here. And if you zero in on the graph, what you'll see is that this analog, which is the last one on this graph here, had the most exciting chemistry that we've seen so far, and that this one underwent oxidation at neutral pH, that's the green and the purple bar here, and actually started to slow down or shut down oxidation at lower pHs. So we're actually pretty pleased with that behavior because, as most of you know, as you're synthesizing and manipulating peptides, it's under acidic conditions, you're cleaving it with TFA, purifying it with some TFA, and so it's actually a good thing that we can we shut down reactivity in those analogs at acidic pH. That's probably happening because we're protonating that dimethylamino as substituent at those low pH. It becomes electron withdrawing and shuts down this reaction. Okay. The other exciting part here is, again, now we actually have two orthogonal N-phenylglycine residues because we've got the paramethoxy analog that gets triggered at pH 4.5 but doesn't react at neutral pH. And on the flip side, we've got the dimethylamino that gets triggered at neutral pH and slows down at pH 4.5. So we should be able to do sequential one-pot oxime ligation with these types of these two residues here, which we haven't tackled quite yet. Okay, so we went back and looked closely. The bar graph that we were looking at was the percent oxidation after 24 hours. So what we did is just monitored it over time a little bit more closely, and we're able to see that after 8 hours, this oxidation is actually complete. So we get 99% oxidation with this analog. But what you'll notice is that we get about 30 to 70 aldehyde oxime ratio. So if you leave this long enough, the aniline that gets released, the one equivalent of aniline that gets released actually catalyzes the reaction, and you get full conversion to the oxime, which gives us this 100% oxime ligation after 24 hours. But it turns out that what's actually happening is we're getting to deoxime only 70% of the time, 30% of the time, right, we're getting to this alpha oxoaldehyde competitive hydrolysis. So we actually got around that by simply increasing the ratio of amino oxy to N-aryl peptide from 1:1 to 5:1. This is the second entry that you see in this table. Now we got, again, 90%, 99% oxidation, but about 90% of our desired oxime ligation product. So I don't want to go too much into the detail, but you'll notice that we went from air to oxygen atmosphere. If you ever want to try this chemistry, read the SI in detail. I gave my student a very hard time to be very, very specific in there. We need to sparge the solution with oxygen for this reaction to go. Don't ask me why. When you have excess amino oxy, you absolutely need to sparge your solution with oxygen to get this to go. All right, and then the last thing that I asked my student to do is to say, well, we've got some fantastically mild conditions, but what about, can we get this reaction to go faster if we introduce a chemical oxidant? And we didn't want to go too harsh in terms of chemical oxidant, so we picked potassium ferricyanide, which has been shown in the literature to be biocompatible, and when we did that, we got the reaction time down to 5 minutes. So to our knowledge, this is really the fastest conditions to get oxime ligation reaction, which typically take closer to 24 hours using standard conditions. All right, so here again, the very detailed SI where you have to sparge the solution. All right, the other thing I'll mention, though, is, again, yes, this is fast, but it is sensitive to the concentration of the oxidant, so there are some pros and cons here. If you increase that concentration to 2 millimolar, we actually see by mass this adduct that seems to be oxidation of the tetrahedral intermediate, right? So that reaction, that oxidation is so fast that it will oxidize a second time before it collapses that tetrahedral intermediate. And again, we haven't isolated that by or characterized that by NMR, but we see that very cleanly by mass spec. If you go above 2 millimolar, decomposition, so very sensitive here to the amount of oxidant. All right, so if we go back to our really mild oxidation condition with just air or just oxygen here, we treated a peptide that contained a methionine residue just to demonstrate how mild this approach is. And we see that during the course of our oxime ligation reaction, we get our desired oxime, and we don't see at all oxidation of the side chain. So that's just to demonstrate how mild this is. Okay, so that was for the dimethylamino substituent, which seems to be really special and really unique in terms of getting reactivity at pH 7. But we also saw some pretty interesting, or thought about some pretty interesting opportunities with the paramethoxy analog. So that analog was inert at pH 7, but we thought if we can find conditions to trigger oxidation in these cases, that might make down the road some pretty cool prodrugs application. If we think about, for example, generating macrocyclic oxime bridge peptides, we could have a situation where you would have a linear peptide at pH 7, but only when it saw reactive oxygen species, for example, would it undergo triggered oxidation to get you to the oxime bridge peptide. And so we did see that if we just use, again, potassium ferricyanide, we can now trigger this oxidation and the oxime ligation formation at neutral pH. So again, really interesting that we now have two different sets of N-phenylglycinyl peptides, and you can pick the substituent that you would like depending on your application here. So the other challenge that we wanted to tackle, I mentioned early in my presentation that oxime ligations are said to be biorestricted because you have other aldehydes in the cells, but now we have a system with the paramethoxy N-phenylglycinyl peptides where we can start to address this problem a little bit better. And so we did this experiment where in the presence of glucose, we treated it under two different conditions. The first one on top is in the presence of an aniline catalyst, but in the absence of potassium ferricyanide, so that should leave our N-phenylglycinyl peptide untouched, and that's what we see. So we see under these conditions, major product formation is the oxime under your carbohydrate. Conversely, if you do this in the absence of aniline catalyst, but now in the presence of your potassium ferricyanide, you can now selectively get to your oxime peptide as the major product, and we don't really detect the oxime on the carbohydrate. So we're starting to address this problem of biorestrictions that's been plaguing oxime ligation because You used to have to start with an alpha oxaldehyde substrate. Now you can start with a different substrate that you can tune in terms of its electronics. Okay, so this is just to summarize what I've been telling you about with aldoxime ligation conditions. The title of my talk is Ketoxime. I'm giving away what I'm going to talk about next. But again, to summarize, when you have a dimethylamino substituent at the para position of your N-phenylglycine, if you do this with oxygen, right, by sparging your solution with oxygen, this reaction will be done in 8 hours in very mild conditions. If you're concerned about kinetics, you want this to go very quickly, you can treat that peptide with potassium ferricyanide, 1 millimolar, and the reaction is done in 5 minutes. If you have a paramethoxy substituent, nothing happens at pH 7 unless you treat it with potassium ferricyanide. If you want to be at under oxygen atmosphere, you have to bring it down to pH 4.5 if there's no chemical oxidant. Okay, so we have this analog, right? The dimethylamino substituted N-phenylglycine analog really seemed to be special. And so we really started to ask ourselves, what happens if I put a substituent now at the alpha carbon? So move away from glycine derivative and start to think about all the other amino acids. Can we get the same type of site-selective oxidation and now get to ketoxime ligation product? I think there's a lot of value in that because it keeps the side chain chemistry at the site of the ligation. And so when we started thinking about that, there was no literature precedence about backing that this could happen, right? Site-selective oxidation of anything other than glycine, there's no literature precedence in contrast to glycine derivative. But we were right in our hypothesis that there's something special about the dimethylamine substituent. So if you, again, just treat that, dissolve that in neutral pH 7, open to air or bubble oxygen, you get clean conversion to an E to Z ketoxime mixture in the case of that dimethylamino substituted analog. We looked at the paramethoxy substituted analog, no reactivity whatsoever at neutral pH, but also at acidic pH, and also with potassium ferricyanide. Okay, so that explains the lack of literature precedence for this, because nobody had really looked at the dimethylamino substituted analogs. And so we're really pleased to see that. And so what we did next was just look at the effect of different R group substituent at disposition. So we looked at methyl phenylbenzyl as a representative class of different side chains. And we see, again, in all cases here, really clean conversion to E to Z ketoxime ratios, but without any other byproducts here. So I'll just point out that, for example, the benzyl side chain analog D here is about 1:1 E to Z ketoxime ratio. The other analogs seem to have one major product, so we're kind of intrigued in going forward to see if we can use that to control conformation in peptides here. Okay, and then at that point we also wondered, just to illustrate the ease and the importance of doing this one pot oxidation followed by oxime ligation, we took a step back and did this in 2 steps. So we took our N-aryl peptide, we exposed it in our first step just to oxygen, pH 7, let it oxidize and hydrolyze to the alpha ketoamide, and then in a second step expose it to the alkoxyamine to get to our oxime ligation product. So first thing I want to point out, again, to highlight the usefulness of our method is as we tried to do this and do the first step, we right away eliminated one candidate. So right away, analog D that had a benzyl side chain just led to a mixture of products if we just exposed that to oxygen. So we got rid of that we couldn't move forward, we couldn't carry forward. And just to kind of pause and kind of highlight the work of other laboratories that have access similar types of substrate, we've got the approach that I'm showing down, the first approach that I'm showing here is by Matt Francis, where he treats his peptide or protein with PLP. The adduct undergoes isomerization ionization followed by hydrolysis. And so this is a very elegant and mild approach, but on peptide, it can be problematic to get rid of the excess PLP, right? So our approach allows to just, again, very simple method, expose that to oxygen. And the second approach I'm showing is treating a peptide with oxone followed by an oxime exchange with TFA, 50 degrees Celsius, so it doesn't tolerate really as many side chains. All right, and so for the step 2, again, I mentioned step 1, we lost one analog, but we carried forward the analog that had a methyl and a phenyl side chain. And here I just want to highlight, really, in reality, the issue with these types of substrates is the ketones are less electrophilic than aldehydes, right? And so that's why it hasn't really been that widely explored or widely employed in the literature. So we did that experiment, and as you can see, aniline does help, right? So that's great. But you can see messier, right? Crude LCMS, lots of other byproducts appearing. And so again, that really illustrates the usefulness of our approach to do this in situ oxidation oxime ligation reaction. I've showed you that this was compatible with methionine earlier, but we also did in the context of our ketoxime ligation reaction other amino acids such as tryptophan, cysteine, serine, etc. And it really works beautifully for all of these different types of side chains, usually greater than 90% conversion to your desired ketoxime. All right, so then we did move on from the small molecule and did end-to-end ligations of 2 different peptides, just to show again that this works pretty well. I draw them in a folded conformation, but again, we haven't looked at their conformation just yet, but one thing that we're really excited about is, in cases where you have clearly one major product, can we figure out if this is the E or the Z oxime, and can we then control the conformation of these peptides based off of sterics on these side chains at the site of ligation? And so another useful utility to this method that we envision would be if we can, again, modulate the R group chemistry at the site of ligation, maybe think about applications down the road in macrocyclic peptide synthesis. We might be able to use that side chain chemistry to modulate the log P properties of cyclic peptides. So we just went ahead and looked at the behavior of a variety of unnatural amino acid that were increasing in terms of number of carbons, and we see by HPLC that we are doing what we should be, right, which is making the peptide more and more hydrophobic. But being in an academic lab, something that really struck me and I thought was really interesting is as we were starting to study these analogs in greater detail, you can imagine solubility was starting to be a little bit of an issue. So we had to start adding in percentages of organic solvent, ethanol in this case, and we started to see dramatic decrease in reactivity. The more ethanol we were putting in, the slower the reaction was getting. I thought that was interesting, and so what we did is we looked back. We wanted to do a comparison between the glycine and the alanine, just to simplify things. And in red is actually the percent oxime ligation as a function of percent ethanol for the glycine derivative, which is virtually unaffected by the content of organic solvent. And in contrast, as soon as you put a side chain at the alpha carbon, that goes down as you increase the percentage of ethanol. So pretty curious, but really interesting behavior. Again, we might have systems where you can orthogonally trigger the glycine if you add enough ethanol, and your alanine will remain inert and things like that. All right, so another intriguing properties that we discovered along the way, we were screening for different the effective pH, and so we were looking at the effective pH ranging from 4.5 all the way to 8 for all of these analogs. Nothing too surprising here. All of these analogs, irrespective of the side chain chemistry, the optimal pH, again, conveniently remains around pH 7. But what was interesting to that story is when my student tried to do pH 8.5, reaction went down, complete shutdown of reactivity. Took her a while to tell me she swapped the buffer salt from phosphate to sodium hydroxide glycine. And so then I went back and asked her, well, is there a salt effect here? Is there something? Is the buffer playing more of a role than we think? And so we looked at, again, just a simple comparative analysis between glycine and alanine. Let's keep the pH constant at 7.5 and just screen a bunch of different salts, right? And so again, same intriguing trend. The glycine, which is in red, virtually unaffected by the salt composition at pH 7, and the alanine analog, you see a lot more variability. It will go, but you see a lot more variability and critical effect of the buffer salt, which might be playing a non-innocent role other than just buffering the solution. Okay, so we think there's actually some really interesting mechanistic studies that we'll be tackling on next. I asked my student to try to do these oxidation in organic solvent for reasons I'll explain in just a second, but perhaps not too surprisingly, any organic solvent under air would oxidize the glycine derivative to the oxalic acid derivative. If we do the same experiment with the alanine, absolutely no organic solvent will get this to undergo oxidation to the ketamine. So there must be a special buffer effect that we will have to try to mimic to be able to get this oxidation to go in organic solvent. The reason why we're interested in that is that it would be a pretty nice route to quaternary amino acid synthesis. We want to move away from amino oxy nucleophiles and move into carbon-based nucleophile, and we need to be able to do that in organic solvent. So there are some intriguing buffer salt effects that we need to understand before we can translate that to organic solvent. All right, so I'll just leave on the note to say that we're really excited about the potential of this method. We're working on just expanding the scope of amino acid side chain at the site of ligation. And so we used to synthesize these analogs via the peptide submonomer procedure, but there's a limited amount of bromoacetic acid derivatives that are commercially available. So we're now moving towards anarylation of amino acid chemistry using Buchwald's catalyst under palladium catalyzed reaction. Working on this scope right now. This works really well. We're using a very electron-rich aryl bromide with a dimethyl amino substituent, and we can nicely actually activate that without necessarily protecting that secondary amine because it's a pretty poor nucleophile. So my students have shown that you can activate that without protecting that nitrogen and get pretty good crude purities and good yields. And again, just expanding the scope of this chemistry seems to be pretty general, works really well. As long as you can get to your N arylation to go cleanly, that shouldn't be a problem moving forward with the Ketoxime ligation. Okay, so on that note, I just want to summarize what we found in regards to Ketoxime ligations. Again, this is actually pretty difficult to do right now because if you go via the ketone, they're less electrophilic, right? So we've addressed this problem by dealing with these really electron-rich N-phenylglycine peptides, N-aryl peptides, and these can uniquely undergo oxidation to ketamine intermediates, which are very electrophilic, prone to get protonated at neutral pH, and we can nicely get in a one-pot procedure to a wide variety of Ketoxime ligation product. And finally, in the case of ketoximes, again, anytime you're dealing with amino acids other than glycine, that seems to be very dependent on the buffer salt composition as well as this organic solvent content. So just being mindful of that. At the end of the day, though, what's really nice is the optimal conditions are just phosphate buffer. Right? So we ended up de-optimizing when we're screening buffers and identified some pretty interesting trends there. But just phosphate buffer, bubbling the solution with oxygen, gets these reactions to go really cleanly. All right, so on that note, I want to thank the members of my lab. We are a relatively new lab. So my very first grad student did almost all of the work here, Kubria Guthrie, and Haley Young is a recent, now second-year student that's picked up and has helped us move this project forward. So thank you for the invitation again, and thank you for your attention.
Thank you, Carolyn, for a great talk.